So thanks to everybody for showing up today. I must say I'm a little intimidated because I'm not used to speaking in the same series with Roger Penrose and Stephen Hawking. So, but I'll do my best. I must say, John, you did a great job in that introduction. It's a little embarrassing in a way. I sometimes wonder if I have a sort of Don Quixote tendency. But now I'm trying to do something useful with my life. So I'm going to tell you about that part. And when you think about the world and what we do as scientists, in particular, well, any kind of science, I would argue we're contributing to the collective awareness. Models that we as a culture and society use to understand our world, to think about the cause-effect relationships, to understand what our options are and where they will lead us. You might think about three levels of awareness that we have. One starts with understanding the external environment. This goes all the way back really for millennia to people like Ptolemy and Archimedes and people like that. But when Newton solidified the laws of gravitation and mechanics, and we now have the ability to, for example, predict the motions of planets quite well. And this becomes a practical thing if you think about a problem like avoiding asteroid collisions, which we know asteroids have hit the Earth many times. They've done enormous damage, comparable to what we might expect from a nuclear war. And so it's a rather serious challenge, actually. And I thought this was something we had licked till I looked into it. I was going to use this as an example of something we really had nailed. And then I started Googling around and I found the NASA's Asteroid Grand Challenge. And they were quite proud of the fact that we've identified 95% of the asteroids that are greater than 1 kilometer in radius. Now, a 1 kilometer radius asteroid would really clobber the Earth. So there's still 5% of them that we don't know are out there. And if you get down to 300-meter asteroids, we've only identified 10%. Those could be pretty nasty too. So even with something like that, we're still actually trying to do things. And interestingly, they're using crowdsourcing and relying on volunteers and so on, because the issue is if we see the asteroid, say 10 years before it hits the Earth, we can predict things pretty well, but we have to actually see it. And we're not looking actively. Another good example would be weather prediction. There, I think that's a success story. We've been actually predicting the weather for more than a century, initially through subjective methods. Around the turn of the 19th to 20th century, people started to be able to make weather maps. And they began just looking at these weather maps and seeing patterns subjectively in what was happening. And professional weather forecasters emerged who would have a catalog of past weather maps, and they would look at the weather map for the day and go, remember, there weren't computers back then. They go, oh, this reminds me of 1925. And they'd flip through their book and find an example of a weather map that matched sort of today's weather pattern, go, well, the wind's 20 degrees off and it's 5 degrees more, and lick their finger, and then they would make a weather forecast that would be published in the newspaper, and people would go on picnics and frequently get rained on. Now, starting in the 50s, in 1950, von Neumann was looking for peacetime applications of the digital computer, and he teamed up with the best meteorologists of the day. In particular, in the end, a guy named Jules Charney led the charge to, they worked hard mathematically, created a simple one-dimensional partial differential equation, which they simulated on the ENIAC computer with the help of John von Neumann's wife, who actually did the programming to put it on the computer. They made a forecast for a couple of weather patterns 12 hours ahead. Now the forecasts, each of them took them 24 hours, so they were well below real time at that point. But those forecasts came out not too bad, and so they declared victory. Billions of dollars got pumped into improving physical weather forecasts. And I was actually around at the tipping point, because in 1980 I was an intern at the National Center for Atmospheric Research, working with Edward Lorenz of Chaos fame. And I asked him, Ed, how are you guys doing relative to the subjective weather forecasters? And Ed was a very mild-mannered guy. He said, well, we're not doing too bad, and we're going to start beating them real soon. And he was right. 1980 was a tipping point, but note it took 30 years to just break even with these guys with their libraries of weather maps. Now, since 1980, weather forecasts are vastly better than they were in 1980. Your picnic is much less likely to get rained on if the weather forecasting service says that it won't happen. Now, so weather prediction we're pretty good at. Now, we're also starting to think about our effect on the environment. And climate change is a great example of that. When you think about it, climate change modelers get a lot of flack, but I think they're doing a pretty good job. They're telling us something that's rather subtle, that's going to happen 50 years from now, that will have very profound consequences on the Earth, and even giving us pretty quantitative information about what we have to do to keep it from happening. So now, note that climate change grew out of weather prediction. They were able to build on a very solid foundation, but we are understanding increasingly more and more about our effect on the environment. But I think the really hard challenge is to understand our collective effect on ourselves. As our world becomes increasingly more artificial, as there are various estimates, but many people estimate that we spend about 40% of the energy that's used to fix carbon on the Earth is ultimately going to support humans. So we're placing a huge load on the planet, and if you just think about your day, you mostly live in a pretty artificial environment. So somehow we need to start understanding better our collective effect on ourselves, which brings us back into social science and the challenge of understanding things in a quantitative way. In some areas like traffic forecasting, for example, we've gotten pretty good. If I'm, these days, if I'm driving back from somewhere at rush hour, I'll pull out my iPhone and I'll check to see what the traffic's doing, and it can reroute me if traffic's messed up. It does a pretty good job of predicting things like that. But now, what about the bigger things like business cycles, for example? Well, so here's an example of a plot of a business cycle. And what you can see is various measures, and I'll come back to some in a minute, things like GDP and unemployment bounce up and down by large factors as a function of time. And you can see that we had some big events, like this is the crisis of 2008, which the Dallas Fed estimated cost the US between $6 and $15 trillion. That's quite a lot of money. That's like half a year of US GDP, and for the world, the answer is certainly a lot more than that, at least many months of GDP, probably a half a year. It suggests if that hadn't happened, we could have all gone on vacation for 6 months and been about even with where we are. Somehow we didn't get to do that. So this is an expensive thing. It costs us as a society a huge amount to have something like that. And it's not just the rich fat cats that suffer. It hits the poor the most of all. At this point, unemployment for Greeks under 25 is at 80%. It's pretty horrendous. It's having a huge toll on Greek society. I have some very close Greek friends. They say it's depressing to be in Athens these days because people are just so dispirited about what's going on. And so here are some examples of what crises due to unemployment, from some arbitrary starting point, you can see it's not that uncommon for unemployment to swing down to as much as 20% lower than where it was before the crisis started. So these things hurt. And I would say there's even a pretty good argument that the Brexit vote might have gone the other way if we hadn't had the crisis of 2008, and that Donald Trump would not have been nominated for president. Okay. Now, 2008 wasn't the only crisis. I already showed you several on this plot here. Financial panics are endemic. This really hit me. It's a long story, so I'm going to give you the short version, but I happened to be in the Treasury building. I was lobbying for something involving the Office of Financial Research, which I played a small role in helping start. It's a remarkable grassroots movement of various scientists and Wall Street practitioners who were shocked by the fact that when Lehman Brothers was about to fail in 2008, we didn't have a clue who their counterparties were and what effect it would have on the financial system if we didn't prop them up. And so a bunch of legislation text for legislation got developed by a committee of which I played a small part. It's about 20 pages. It actually went verbatim into the Dodd-Frank bill and got enacted. And it was an office to collect all the data together and allow us to really think systematically about markets. Now, I was in the Treasury building actually to lobby the Deputy Secretary of the Treasury to appoint somebody who had a strong science background to the post. I was not successful, but that's another story. But as I was leaving, I started to walk out of the building, and I noticed there were these portraits of the past secretaries of the Treasury. So I started, looking at them and reading the little inscriptions below, and it's kind of, as I was going backwards in time, boring. But then I got to the ones that were actually dead when the inscriptions had been written, and then the inscriptions got much more truthful and much more interesting. And I, noticed that about every other one, it would say either did a great job of dealing with a financial panic of X year, or did a terrible job of dealing with a financial panic of X year. And after I got out of there, I actually looked it up and I made a list of the financial panics. As you can see, there's a lot of them. They were routine events back in the old days. I can't resist throwing some of these pictures in just for the graphics. Cartoonists have been good for a while. A particularly important panic was the panic of 1907 that was triggered by events in copper markets. It looked like the whole economy was on the verge of collapse, and J.P. Morgan rounded up all the big players on Wall Street, put them in his office and basically gave them orders about what to do to prop up the financial market. This ended up being hugely controversial because people were understandably suspicious of a guy like J.P. Morgan. Did he profit from it? He actually later felt quite, let's say, frustrated because he felt like he'd done the world a good turn. But this led, finally, for the U.S. to start a central bank, the Fed, in 1913. And by the way, since then, you'll notice, if you go back and look at my list, panics up until the Fed was formed came about every little less than 8 years on average. Since the Fed was formed, well, we had a doozy, obviously, in 1929, and another big one up here, but they've been somehow bigger but less frequent. So it seems that it has made a difference. But bigger but less frequent, they're still happening. We still don't really understand as they're coming on us, we don't understand they're coming, and it's still debated how we should deal with them once we're there. Witness debates about austerity. Now, given this, you might think, just if you go back and do the numbers, if we're talking, say, $50 trillion that a crisis can cost us, well, how much research should we be doing to deal with that? Well, just to take some numbers, the National Science Foundation for Economics and Social Science in the United States is $30 million a year. Not much. U.S. Federal Reserve, in its like 12 branches, spends a total of about $500 million. Some fraction of that goes for research. And I made a ballpark estimate of how much money gets paid out to academic economists throughout the world. Maybe it's $1 billion. So, that's not much when you think that the mistakes that are happening can cost us $50 trillion. $50 trillion, that's 5 times, if I can, 10 to the 13 versus 10 to the 9. So we're talking about the order of 10,000 or 50,000 difference. So even if there's low odds of making things more successful, it looks like investing more money in economics should be a really good investment. I'll note, just as a reference point, $1 billion is about what the US budget is for polar research. Now, I'm a great advocate of polar research. I don't want them to cut that one little bit, but it does seem like a dichotomy to me. Now, but you ought to ask, of course, would this more funding be effective? And there's several arguments that you might make to say that it's not. Maybe the economy is inherently unpredictable, for example. Maybe there's fundamental limits like market efficiency that say it can't happen. Or maybe social science is a quixotic quest in and of itself. Maybe people can't be described by laws. People like George Soros, who ultimately pays my salary, have suggested that that's true. Now, he's still paying my salary, so he must not think it's a complete lost cause. And now maybe there's another effect, though, which is maybe the culture of economics doesn't scale with more funding. And I'll note that they aren't unlike, say, meteorology, where you can bet every budget cycle they're there in Congress saying, we need more money, we need supercomputers, we need better satellites, we need better measuring instruments, we need more money. Because we're always pushing the limits of what big science can do. Economics is not doing that. Now, I just want to note that these arguments are only valid if they're really strong, because remember, there's that factor of 10,000 or 50,000 there. So to think about this question, let's step back now and let's think about the standard template for an economic model. How do economic models work? So I'm going to teach you economics in about 3 minutes. Challenging task. But it's only made a little easy in that economic models all follow more or less this template. So what do economists do? They assume that agents have preferences and beliefs. The preferences might come in the form of a utility function. The beliefs might come in the form of something called rational expectations. So they optimize that utility function perfectly. Then they just assume there's a fixed point equilibrium where agents will maximize their preferences according to their beliefs. And so then they compute what everybody's actions are, and then from there you can compute prices and quantities and all the other things that come out in an economic model. And so this program's really hit its stride back in the 50s, maybe reached its peak about 1980. And then since then, the program in economics has been to modify these assumptions one at a time. So they, for example, in the old days, they would assume utility and perfect rationality. That was everybody would know everything. They say, no, okay, maybe not everybody knows everything. Maybe there's asymmetric information. Maybe there's institutional constraints, so there's some things that people can't do. Maybe only some of the agents are rational and a few of the other ones are rational. So they play with these assumptions one at a time. But the thing that is invariant, and they almost always do, when I say they, I'm referring to the sort of mainstream, because there are some rebels out there like me that are challenging this. But this fixed point assumption is something that's invariant in this. So I'm going to examine that as the first thing I do in this lecture. And before I go forward, I just want to comment that there are many kinds of equilibrium. I was educated as a physicist, so you immediately learn about forces balancing. It's this trivial kind of equilibrium. Then you learn about thermodynamic equilibrium. It's a bit more subtle. Energy flows are balanced in a detailed way. But in physics, we know what equilibrium is. We develop a framework outside of equilibrium, and then we can test to see whether equilibrium's an appropriate assumption or not. When it is appropriate, it's great because it really simplifies everything and you can do the calculations really well. I've already referred to dynamic equilibrium. That is the notion of a fixed point, so where things don't change, which underlies almost all economic theory. And strategic equilibrium, which is specifically what they're talking about, where all the agents fully take each other into account and do that in order to consider their reasoning. And in fact, in economic models, one of the difficulties, well, it's a good thing and a bad thing, things are greatly simplified by assuming equilibrium off the bat, but you're left wondering whether the equilibrium assumption is valid. The pinnacle of economic theory that this has led us to are what are called dynamic stochastic general equilibrium models, and what Andy Haldane has dubbed a rocking horse economy. And the reason I say that is if you think about the analogy to physical equilibrium, imagine that you have a rocking horse and you bang that rocking horse with a hammer. So you knock it away from its equilibrium, so now it's rocking, and it starts to damp down again, and then you hit it with a hammer again and it rocks again. So that's a little bit the assumption. The assumption is if it weren't for shocks, the economy is in equilibrium, but Zeus throws shocks down from on high. The shocks could be technological shocks because some technology has gotten better. They could be behavioral shocks because people have changed their attitudes towards things like they become more impatient for some reason, so they're discounting differently than they used to. The shocks knock the world out of equilibrium, the world moves back towards equilibrium, and the shocks hit again. And these models spend a lot of effort in diagnosing what these shocks are and trying to make some predictions. Now, to see the kind of thing that they're talking about, here's another picture of a business cycle. In this case, we're looking at the logarithm of gross national product, and over about a little more than half a century. And we're looking at the deviations around the mean trend, which is upward. So there's already an art in how you do that stuff. And so under this view, all these fluctuations are driven by these shocks hitting the world, which is always trying to go back to that mean trend. Now, I want to comment, and I'll come back later to say some more about limits to prediction, but when you make a model like this, you've inherently said that the noise is doing a lot of the work, because you're saying that the main explanation for this whole movement in something like a real business cycle model, I find that a bit of a strange name, is that these shocks are hitting, and the shocks are something that economists a priori cannot predict. It's always worth remembering that, by the way, whenever somebody talks about noise is typically not fundamental. I mean, the only fundamental source of noise that we know of is measurement in quantum mechanics. Everything else just amounts to our ignorance. And not that noise models aren't useful, but they're inherently self-limiting. So now, why would you expect that the economy might not be in equilibrium? Well, first of all, beliefs and outcomes may not be consistent. And when you dig in to equilibrium theories, you see that consistency between beliefs and outcomes is a deeply important part of what is going on in equilibrium. And as I've already suggested, the strategy dynamics may not settle into a fixed point. So to illustrate this, I'm going to begin by thinking about the strategic contest where people are reasoning, and I'm going to use something called a Keynes beauty contest. Now, in Keynes's day, papers would publish, this is an example of a page of a newspaper from the time, they would publish pictures of women. I admit this is a very sexist thing to do. I don't think they ever did this with men. And they would then ask people to rate how attractive they thought these women were. And people would then rate them. And then if you voted for the choice that was most popular, your name could be drawn out of a hat and you might win a vacation or something like that. And but Keynes pointed out that what matters there's no inherent measure of which women are the most beautiful. The criterion is to guess what other people will think is most beautiful. And he pointed out that the stock market is very much that kind of thing. It's not necessarily what makes prices go up isn't what company is the best company, it's what company do people think is the best company. So that was the context of his doing this. But I'll now give you an example of a different kind in that spirit. You're asked to name a number between 0 and 100. And the winner is going to be the one whose guess is 2/3 of the average guess. So I want you to think about this for a few seconds. Try and think, what would your guess be? Now, I've done this in the past by polling people, and I've discovered that it's a bit of a dangerous thing to do because it can be a little embarrassing once I explain what's happening. So I don't want to embarrass anybody. Also, I can't make my snotty remarks because I really wouldn't want to offend anybody. So just think about it. Formulate your guess. I want everybody to pick a number. However you're going to do it. All right, now, let me show you what about 30,000 Danes did. Now, this was published in the newspaper, so they had more chance to think about it than you did. And you can see that, the guesses, there are people who actually guessed 100. Now, let's go back and think about, you wonder a little bit, okay, I mean, this kind of might explain why people are actually going to vote for Donald Trump. Okay, let's suppose all of you but one guessed 100. Okay, if everybody guessed 100, then what would the winning guess be? 66, right? 2/3 of 100. So obviously, anything greater than 100 is a loser. So all those guys, there's quite a few of them, either they didn't understand the game or they really weren't thinking. Now, let's suppose then you go, okay, I'll guess 66, but you go, well, 66 is pretty high because other people aren't total dummies either. And why would they all guess 100? Well, okay, so maybe they would guess 50. And now let's take 2/3 of that, so that'd be about 1/3. So you see there's actually a peak there. But then you might go, well, okay, suppose people guess that, then I'm going to reason one more. I'll assume that's the typical guess. And so, in fact, that's the winner around just above 20. So, but note, if you were an economist and you were trained to think about rational expectations, you would have iterated this process and you would have guessed the Nash equilibrium, which is 0. Because that's where you end up if you assume that everybody's really smart. If we were all smart and we all knew that everybody else was smart, we would just go to 0 and there would be a fixed point equilibrium. Everything would be peachy and it would be easy. So my snotty remark is, okay, these people are obviously idiots and these guys are idiot savants. So, all right, my snotty remark. Okay, so when is this assumption justified? So I'm going to show you an example of some work we did to test this in the context of game theory. The players can make one of several possible moves. So a game is something where players make moves. So it's like the games you're familiar with. At each turn, players receive payments according to the set of moves of all players. In other words, if on that turn, Martin makes a move and I make a move and Alyssa makes a move, we make move number, Alyssa makes move number 1, I make number 2, Martin makes move number 3, we then look up in a payoff matrix what our payment is, and each of us gets some payoff that may be quite specific to each of us. And so that payoff matrix defines the game. Then we're going to play that game repeatedly. So we're going to play it again and again so we have a chance to learn from it. So, and by the way, I think if we played that Kane's Beauty Contest game repeatedly, we would have seen a progression toward 0. But we're going to make the players learn their strategies. Unlike the, well, I guess I have, excuse me, have this on my next slide. There's a standard theory by Nash which says that there's always a fixed point in a game like that. There's always an equilibrium like the 0 equilibrium in the beauty contest, as long as players can choose moves and introduce an element of randomness to keep the other players guessing. As long as they can do that, there always exists a fixed point. But Nash didn't prove it stable. So we don't know that that's behaviorally what people are actually going to do. And the experiment I just showed you suggests that that's not what people typically do. But what do they do? Now, okay, let me give you a little bit of intuition. So the first thought I have on this is simple games should be easier to learn than difficult games. So I'm reminded of when I was about 9 or 10, on the playground, we started playing this game called tic-tac-toe, which I think in Britain you call noughts and crosses. So you make a little 3x3 grid, you put X or 0, you try and get a diagonal, horizontal, or vertical line of connected things. Whoever does that first wins. So at some point, I figured out that I could be 0, and I could always block the other guy from doing it, so I could always at least get a draw. And so for about a day, maybe, I felt like a real hero because I was just cleaning up. And then all my friends figured it out, and the game became completely boring. We quit playing it. So that's a good example of, tic-tac-toe is a simple game. Children learn the Nash equilibrium. Now, what about more complicated games? Say, take chess. So now I'm going to tell you a little joke. How did 2 economists play chess? Well, so there's a random element to chess. You begin by choosing white or black. And then they choose white or black, and then they argue about whether white or black wins under the Nash equilibrium of the game. Now, why is the joke a little silly? Well, because we don't know what the Nash equilibrium of the game is. It is a deterministic game once you've chosen white or black. Now, I have to tell the corollary of the joke because I'm a physicist, so it's rude to tell jokes about economists without telling a joke on your own tribe. So how do 2 physicists play chess? Well, they get quite drunk, and they start moving the pieces around randomly, and they argue about whether the game is more or less interesting under scalings of the size of the board and the number of pieces. So you'll see from what I'm about to present that I'm a physicist. Now, so what we did is we said we wanted to understand generic behavior, and I did want to make sure that my comment was registered, that we're not the first to think about this issue. Lots of people have worried about this from the beginning. In fact, von Neumann himself was quite critical about game theory for its emphasis on Nash equilibrium. And in particular at Oxford, we have a couple of people who have been pioneers in this, Peyton Young and Vince Crawford. So other people have thought about this. But we took a different approach. And we really wanted to understand what's generically true. So we constructed games at random. So remember, there's this payoff matrix that determines how much you get paid under the collection of moves that get made. We put random numbers into that payoff matrix. Once we put those random numbers in, we keep the payoff matrix fixed. And then we give the players a learning algorithm and we have them play. Now our goal is a bit like, we want to characterize the behavior a priori as much as we can. In other words, we want to know, are there some rules of thumb that might tell you in advance whether a game's likely to converge to an equilibrium or not? An analogy can be made to the Reynolds number in fluid turbulence, which is a number, the ratio of the shear stress to viscosity, non-dimensional number. If that number is around 1, then I pretty much know the fluid's laminar. That is, the dynamics sits at a fixed point. On the other hand, if that number is 10,000, then I'm virtually certain that the fluid flow is going to be highly turbulent and chaotic. So we're looking for something a little like that. Now, so we actually did something. We didn't just populate these payoff matrices completely at random. We chose payoffs so they were normally distributed, and we constrained the payoffs, and we began by studying 2 players, and then we'll go to more players later. So when we have 2 players, we constrain them so that we have a parameter gamma that involves the relative payoff matrices of the 2 players. If gamma is 1, the payoff matrices of the players are identical. So if I'm playing Martin, his payoff matrix and mine are exactly the same. If I win, he wins. If gamma is 0, if I win, he might lose, completely uncorrelated. And if gamma is -1, we have a zero-sum game. If I win, he loses. So that's an important parameter we discovered. We also chose a learning algorithm in which players learn their strategies using an algorithm called experience-weighted attraction. We chose this, under this algorithm, players choose their strategies probabilistically. So if I was saying rock, paper, scissors, I would have a certain probability of playing rock, a certain probability of paper, certain probability of playing scissors on any given turn. Those probabilities can change dynamically in time, but on every turn I'm going to roll some dice that are going to be balanced according to those probabilities to determine how likely I'm going to select something. And we chose this because some economists had done experiments and shown that it's a pretty good model for how people actually behave in games in a laboratory. It was also analytically tractable for us to study it. Now, this learning algorithm has a parameter alpha that determines memory because the probability of me making a given move is dependent on how well it's been working in the past. If alpha is 0, the past can be infinitely long. As I just accumulate more and more data, and something that happened years ago is equivalent to something that happened the last turn. If alpha is greater than 0, then I pay more attention to things that happened the last turn than things that happened way in the past. Now, what did we find? And I should say one more comment that's important. Being physicists, we chose the limit where there's lots of possible moves. We looked at really complicated games. Now, we did that because that allowed us to go into the thermodynamic limit where we can actually compute stuff using cool analytic techniques. So that my collaborator, Tobias Gala, is an expert in. So what did we find? What we found is what happens really depends on the parameters. This parameter alpha that determines memory of the strategy is important. And the parameter gamma is also important. And there's a big region here where you just converge to a unique fixed point that's close to a Nash equilibrium. So that's very much like what the economists are typically assuming. This is the zone where traditional economics is okay. But then we found this chaotic zone over here that I'll tell you more about in a minute. And then so this happens, by the way, when gamma is less than 0. So the games are competitive in the sense that if I win, Martin tends to lose. And so we saw these chaotic cases here where there was no convergence to a fixed point. When gamma is greater than 0, we saw multiple fixed points, which in the large state spaces we were looking at where each player had 50 moves, there could be hundreds of these fixed points, and which one you converge to depends on exactly where you start. So there's multiple basins of attraction in the dynamical system that corresponds to the learning dynamics. Now, what's going on in these chaotic cases? When the cases, so we saw lots of things. So we saw, for example, now here I'm going to pick 3 out of the 50 strategies, or I should call them 3 out of the pure strategies as another term, 3 out of the 50 possible moves. So this is the probability of making that move as a function of time. And what you can see in this case that corresponds to these parameters, there's just an oscillation. So the players are just going around in a loop. History is repeating itself. And they're in the state space where you take a couple of the moves and you just project things out onto that axis. You see an attractor whose dimension is essentially 1, and they just go around in this loop. In other cases, you see things like this, where you see what we're able to do to tell for using various techniques is a low-dimensional strange attractor. And in other cases, the dimension of that attractor gets bigger and bigger. It's still a strange attractor, but the dimension gets bigger and the behavior gets more and more random. Here it starts to just look like a ball of yarn. It's to all intents and purposes a random process. And though there's some interesting things going on here, if you look at one of the strategies here, this strategy is sometimes played with a probability approaching 1. You notice this is a logarithmic scale. And at other points, the probability of this strategy being used can be 10 to the minus 20, virtually never used. And then it can come back and become very popular again. So there's an automatic generation of fads of different strategies being used in this world, which has a certain realism. Now you can ask, what happens when you go to more players? What changes if instead of 2-player games, you have multiplayer games? Now, let me first make the remark that we were able to analytically calculate this blue line to very high approximation. So we were quite proud of that. I mean, it takes 20 pages of hard math to do that, but it matched pretty well with what we did in the simulations. Now, what about when we have more than 2 players? Well, when you have more than 2 players, by the time you get up to, say, 10 players, it becomes really hard to simulate this for more than 2 moves. So we can't even go into that high move zone again. So here we really had to rely on our theory. We tested our theory as best we could. We pushed the theory out there and we showed that the area of the chaotic zone increases as the square root of the number of players. And so in fact, what happens is, as you add more players, this boundary just translates itself over like this, and chaos takes more and more of the parameter space, as does this complicated region. And in the limit where you have lots of players, you never see the classic Nash fixed equilibrium. Now, if you're an economist, this should make you a little nervous, because this is suggesting that when there's a lot of players in a complicated game, it may be the generic case. In fact, I would argue you have to justify that you're going to use a model that just has a fixed point, because what it means, if you assume a fixed point in something complicated, like I would say the stock market is a good example, you're approximating this big ball of yarn with this complicated dynamics of the strategies by a point sitting in the middle of this. Now, it's a point with some noise. As I said, this is, for many practical purposes, a random process, but I think there can be key differences. Like, as I actually showed in one of my earlier papers, you can sometimes take advantage of this when there's chaos to make a prediction about the endogenous dynamics. And I think it can be insightful as to the type of the model. And by the way, as a side effect, we saw, here you see the change in the total payoff as a function of time. You see these periods where things are pretty quiet. You see periods where things are quite noisy. This is very reminiscent of what you see if you look at returns in a stock market, something called clustered volatility. This was a surprise, not something we expected to see. Now I have to add some caveats, and I'm worried about running out of time here, but what happens with other learning algorithms? Well, we've explored some. Like we've explored some versions of the kind of level K learning that you saw people using in that beauty contest example. You can ask whether the ensemble of games we're choosing is representative. You can ask about games with just a few actions, like 2x2 games. Marco Pangalo, my graduate student here in Mass, has been looking at that, has actually made a classification of what happens under all 2x2 games, and showed that while chaos is now much less likely, there is still a zone where chaos happens even in 2x2 games. Now, so how do you cope with this kind of nonlinear, non-equilibrium behavior? If you throw out those fixed point models, what do you do instead? So I would argue that you have to go to simulation, because if you want to make any kind of realistic models, you end up with nonlinear equations, and nonlinear equations are typically not solvable via any other means than simulation. And just as a note, computation has revolutionized the physical and natural sciences. I think it accounts for most of the progress we've made over the last 50 or 60 years. And this was really driven home to me, this concept, the importance of nonlinear dynamics or nonlinear equations in general. When I was a graduate student, Stan Ulam came to the physics department at UC Santa Cruz where I was studying and gave a lecture in which he began by apologizing for using the term nonlinear. And he said, I'm apologizing because calling an equation nonlinear is like calling an animal a non-elephant, because most equations are nonlinear. And we've been blinded to that fact because up until now, and Ulam was one of the up until recently, all we could solve were linear equations. So we were like the mathematician sitting under the lamppost looking for our keys, because that was the only place there was any light, even though we knew we've dropped the keys somewhere else. And so now, Ulam was actually one of the first people to use computers to look at nonlinear systems. The very first example of simulating something on a computer in 1945 was the Fermi-Pasta-Ulam experiment, in which they put masses with coupled springs on the computer, and they expected just to see ergodic behavior. They were just trying to confirm something that was standard in statistical mechanics. They thought the energy would be equipartitioned among the modes of oscillation, and instead they saw solitary waves propagating back and forth, the opposite of what they predicted. And so now, social science, I would argue, has not benefited as physical and natural science have. I think there's two reasons for that. One is the elementary processes are not well understood, so it can be harder to put things on the computer. And secondly, there's different cultural attitudes that has to do with, I think, symmetry breaking in the history of economics. But I'll maybe come back and say a little bit about that at the end. Now, I want to give you another example from my work of how you can deal with out of equilibrium behavior that relates to something called leverage cycles. And leverage cycles, as we discovered in 2008, are one of the most important examples of the dynamics of systemic risk. They were foreseen before 2008 by people like Hyman Minsky, who wrote about them in words. He didn't have a mathematical model. And his basic story is that during calm times, people get complacent, they compete for profits, leverage creeps up. I'll explain what leverage is in a minute, but people take more risks. And then as leverage gets higher and higher, eventually some negative shocks are going to hit and they're going to cause a crash. John Giannakopoulos, who I've collaborated with on many papers, also had a theory of leverage cycles. He actually coined the term, involving heterogeneous investors, that optimists use more leverage. Bad news comes along, that wipes out the optimists. And because the optimists were baked into prices before, then there's a big downward spike because they get removed from the picture. Now, I'm going to show an even simpler model than either of these two that was developed with Christoph Eimans, who was my graduate student here and is now a postdoc at the LSE. So it involves leverage. Now, what is that? That involves buying assets with borrowed money, and the leverage is a number that's the ratio of the value of those risky assets to how much money you actually put down. So if you buy a house and you make a down payment that's equal to 20% of the price of the house, that implies a 5-to-1 leverage because the value of the house is at the moment where you purchase it 5 to 1. This ratio is 5 to 1. Now, of course, after that, the value of the house may change and your leverage may go up and down. And it turns out that's very important. Our model is a model it's targeted at explaining rather ambitiously the Great Moderation and the subsequent crisis. What happened historically is that stock market prices went up over a period of a decade or so. Stock market volatility went down, and leverage for assets of US broker-dealers, speculative traders, went up and actually skyrocketed in 2008, then crashed down, sent volatility really high. The stock market came down with it. So can we explain this kind of behavior from a simple model? Now, I have to say, before I present this model, we began by making a rather complicated model. We had a bunch of banks and a bunch of assets, and the banks were managing things, and initially we didn't have any risk control. And we said, what happens when we throw in Basel II, the regulation that banks are supposed to follow? And we saw the whole economy going up and down in this big oscillation, and we said, holy shit, what's going on? And we began simplifying the model, and we simplified it down to the model I'm going to show you here. So when we stripped things down to the essence, all we needed, it turned out, were two agents, a bank, which you can think of as any agent that's using leverage, and a fundamentalist who is an agent who isn't, and who buys undervalued assets and sells overvalued assets. We assume there's one risky asset plus cash, and we make 4 assumptions. We assume the bank uses an exponential moving average of historical volatility to estimate the expected volatility going forward. So what does that mean? That the bank, if you go back to the kind of picture I showed you a moment ago, the banks who are leveraging are looking at this time series, and they're using a historical average of what this has done over the last couple of years or so in order to decide how volatile things are likely to be going forward. That's actually a very reasonable thing to do because volatility is pretty persistent. And so the future is, in general, like the past. There can be spikes, as we see here, but most of the time it's a pretty good rule. And I stand on that assumption because I can just tell you, you survey what people do. They do that. When I was at Prediction Company, the firm where Norman Packard and I formed after we didn't get rich playing roulette, we started an investment management firm. They don't throw you out for winning, and we did pretty well. And we did this too, like everybody else. Basel II risk management, this is a standard thing. Actually, this came in while we were at Prediction Company in the late 90s. Use something called value at risk, where you set the leverage target. I'll come back and explain what that is. We use a standard assumption about price formation, supply equals demand, so we find prices that way. And we assume this fundamentalist buys undervalues assets and vice versa. So the diagram of the model looks like this. We have a fund, we have a bank. The fund detects a mispricing. We just assume a fixed valuation. It updates the portfolio weight. There's a little shock that keeps knocking things out of equilibrium. So we are using a little bit the same trick as that dynamic stochastic general equilibrium model. But with the important thing, we don't enforce strategic equilibrium in this model. And the bank similarly updates its risk estimate, enforces a leverage constraint, and we form prices. And now let me mention a key fact, which is that for a passive investor with leverage greater than 1, like the bank, if prices drop, leverage goes up, and vice versa. Now, so why is that? If you look at the formula for leverage, with prices drop, it affects the risky assets. It affects the equity, which is the assets minus the liabilities. It affects these assets by the same amount, but because you're subtracting off liabilities in the denominator, this effect is bigger, and so you see an amplification. So when prices drop, leverage goes up. Now, if you're under if you have to control your leverage, this becomes destabilizing because now your leverage is higher than it should be. So you're above your target, so you have to sell assets to match your target. So notice your risk control is now destabilizing the market. So although it's a sensible thing for you to do as an individual, for the world as a whole, if everybody is doing this, their price impact is destabilizing thing because they're buying into rising markets and selling into falling markets, And in fact, when we originally tried to make this model, we tried to make it with just banks, and it just blew up because it's just destabilizing. We had to put the fundamentalists in there even to stabilize things. Now, just to explain value at risk, that is AKA Basel II. Value at risk is a little rule that mathematically looks like this, whereby when volatility increases, your leverage decreases. And according to Basel II, it would follow this blue line, where this B parameter here is -0.5. And there's some limit, but up to the limit, if you set the limit to 0, you can see it's just, your leverage is just going as 1 over the standard deviation of volatility. Very sensible thing to do from a microprudential point of view, because if the world's riskier, you should take less leverage and take less risk. Supported and endorsed by the establishment. By the way, this dashed green line would correspond to constant leverage. Now, what happens when we run this model? Well, in one regime, when we make the banking sector small, we see random oscillations. And I should mention this model is now a dynamical system. It's about 6-dimensional. And it's stochastic in general. So here we're running it, and you see that things are kind of randomly varying around some price, but not much is happening. The leverage is fluctuating a bit, but not much is happening. Now, suppose we make the banking sector bigger, and what does that mean? Well, when the banking sector is small, it means we don't give them much money, or that we don't let them take very much leverage. But if we let them do either one of those things more strongly, then we see something happening like this. This is that oscillation I already mentioned, where prices are slowly building and then crashing, and slowly building and then crashing, and leverage is similarly slowly building and crashing. Now, interestingly, we can turn the noise completely off. If we turn the noise off, now we go to a fixed point in the small banking sector version. Things just get flat. But for the large banking sector, we see an oscillation. And in fact, this oscillation we can show as a chaotic oscillation, where things go around some loop in a space that involves price and who owns the asset and what the perceived risk is. And you can see there's some kind of complicated behavior over in this part. But if you slice this thing, you see the characteristic fractal structure that you expect from a low-dimensional strange attractor. And by the way, there's a hyperbolic fixed point, for those of you that have taken dynamical systems and know what that means, that's driven by this place where the leverage of is going to infinity, where things get really unstable in this model. Now, let me just discuss a little bit what happens as you vary parameters. There's 2 key parameters there. One is alpha, which is controlling the risk of the individual agents, and B, which is controlling the risk policy that we let them follow, because we're interested in, what are the alternatives? And the phase space looks like this. So Basel II corresponds to -0.5 for this parameter B that makes the risk control more or less pro-cyclical, it's called. And as long, and this corresponds to varying alpha, but I plot leverage instead because that really simplifies the plot. And what we see is there's a region here where things are nice and stable. This is where the fixed point equilibrium works. There's a region up here where things oscillate. And the boundary between those involves a Hopf bifurcation. Things happen very suddenly. Excuse me, it's a flip bifurcation. Things happen very suddenly. You suddenly go from a fixed point to a finite amplitude oscillation. And as a regulator, you really better understand this, because obviously the consequences could be serious. Now, does this explain the great moderation in the crisis? Well, I wouldn't want to argue that it is the explanation. But on the other hand, it could have caused it. And I forgot to say something essential back here, which is that when you look at this oscillation, here the time axis is not arbitrary. We've calibrated this model. These are measured in years. So these run-ups automatically come out with a period of around 15 years. And the levels of leverage that trigger this to happen are quite plausible for what happens in the market. So that is, we get a reasonably good match with what's actually going on. And the model very clearly says the leverage was too high in the period leading up to the crisis. So it could have caused the great moderation in the crisis. And therefore, the housing bubble may have just been the spark that made this happen. Now, How can we do things more realistically? Well, we've been working on making what are called agent-based models. What I just showed you was a very simple example of an agent-based model. In general, if you want to make things more realistic, you've got to do better than that. You're not going to get an accurate model of the economy with a model that just has 2 agents and 1 asset. We're not that lucky. I argue that to surmount the fundamental problem of macroeconomics, which is that if you go think about the business cycle I showed you, there's only about 15 well-observed business cycles in the history of civilization. The ones in the distant past are probably not completely relevant to what's going on now. So we have very limited data to use to calibrate models. We have to, I would argue, make good fundamental models. We can't just use statistical models because the curse of dimensionality blocks us. And we've got to use microdata to validate them. Now I'm out of time, so I'm not going to say much about this, but just to say if you look at something like climate models, it's been key that they're not just looking at time series like global mean temperature and global carbon dioxide. They're looking at details about the weather patterns they predict, and they can show they can do things like join Tierra del Fuego together with Antarctica. Their simulations, the world suddenly gets vastly warmer than it is now because they block the Antarctic current, and you can look back in the record and see that that's in fact how it was then. Now, my vision of the economics of the future would be a simulation of the economies of the major countries of the world. We'd get the micro big data inputs directly off the internet. We might even couple this to other social models. We'd have teams focusing on each components, on households, firms, banks, etc. And they would be monitoring, using the internet, whether their models are really being followed. I'm going to skip over this because I want to wrap up pretty soon. Now, how well do I think we can do that? Well, we're not going to do that perfectly because there are things like market efficiency. Market efficiency is a self-organizing process. I'll say a bit in a moment. It limits the predictability of tradable assets. I've already alluded to the fact that I think in the real world, we see something that's very close to turbulence in financial assets and in the economy. And in fact, there's a beautiful paper in Nature from about 2006 just pointing out that as you vary this, if you do a matchup of the statistics of fluid turbulence to those of the financial system, the matchup is quite accurate. I don't think we're going to be able to make detailed forecasts about the future of the economy, but I do think there's a lot of stuff we can predict. And that is, there's a lot of information we can compress by making better models that we can use to formulate policies. It's back to this question of social science versus physics. You know, unlike atoms, people can't think. That does put, sorry, people can think, sorry. Sometimes I think they can't, but yes, people can think. What scientific limits does this impose? Well, it does impose some limits. Economics is a hell of a lot harder than physics. I've done both, so I can vouch for that. But that doesn't mean everything's impossible. That doesn't mean you have to just throw up your hands. And I would point to the consistency of psychological experiments. There's a lot of psychological experiments. If you put people in a certain situation, you can make a pretty good prediction that 70% of them will do one thing and 30% will do another thing, and it holds up fairly consistently through time and so on, with some variations, cultural variations and so on. I think big data empowers us to do incredible things that we couldn't do before. I already mentioned the example of traffic forecasting, which is a sort of trivial example. It's a bit frustrating if you look at how we go about running the models that are actually run to understand economies. They're run through a methodology based on national accounting that was developed in the 1950s and has evolved only little since then. It involves surveys, it involves boiling everything down into aggregate data. It involves the numbers coming out often a year after they were actually, the events are actually happening. I just think we can do infinitely better than that. Now I want to say a bit about market efficiency and then conclude. The hypothesis of market efficiency says that markets are inherently unpredictable. Now, when I heard about that, my immediate reaction is, okay, I've got to go try and predict markets. And, and I think we and many others have since then showed that actually markets are somewhat predictable enough to make some money. But even, the good firms like ours, we were right maybe on 55% of our bets and wrong on 45% of them, so it's still pretty noisy. So I don't want to say that this is easy. The world is actually close to being market efficient. The question is, I argue, how much difference does it make? How much difference do these inefficiencies make? Well, they make an important difference. They put a lot of money in my pocket. Okay, but in general, for society, is this something we ought to care about? And I argue that we should, because there's a catch. You can see automatically markets can't be perfectly efficient because market efficiency requires arbitrageurs. You've got to have people out there to exploit them. But if there's no inefficiencies to exploit, they'll all go home, and so the market will be inefficient again. So there must always be some residual inefficiencies. And so the way I would put this is markets are efficient to first order, but necessarily inefficient at second order. And I think this has important consequences. I wrote a paper back in 2002 with a market ecology hypothesis. And the hypothesis is that we need to think about what the strategies that agents are following, what are these inefficiencies that they're feeding off of, how do these different kinds of agents interact with each other, and what happens. And I did a lot of stuff in that paper where I basically mapped the financial system into the theoretical framework that's used in ecology and showed that you got all the same things that ecologists have worried about in financial systems. And I'm working with Alyssa Kleinendenhaus and others to try and use these ideas to actually get better models for understanding financial risk, because one of the key hypotheses here, the last one, is that imbalances in the market food web can drive crises. When market ecologies get out of balance, strange things can happen, and I would argue this is what happened in the crisis of 2008 when subprime mortgages and strange new derivatives got way out of hand. Now, there's a lot of challenges to doing this kind of thing, to making realistic models. There's a group of us here who are working on this, most of whom are in the Mathematical Institute. We're trying to create the key building blocks. We're trying to take advantage of the collective wisdom that's been accumulated by the small cadre of people that are working on out of equilibrium agent-based models to understand how to do simulations in economics, make them really simple and easy to use. We have an open source project. Any of you can track what we're doing, join it. All the code's available as it's being created. If you have programming skills, please, and you're interested in this kind of thing, please contact us and we'll sign you up. We're trying to create a library of standard models that anybody who wants to join can build on to deal with the problem that these kind of models actually are time intensive to create. And if you have to create everything from scratch, it's hard to accumulate progress because a typical graduate student will spend several years just writing software to get to the point where they can do something useful. And we're focusing on 3 use cases at the moment: housing markets, insurance industry, and bank stress testing. Now, to conclude, I apologize, I haven't said anything in this lecture about long-range evolution, about growth, innovation, the things that actually cause long-term structural change in the economy. There just isn't enough time to talk about it here. Let me just say that's another component of the work I do. We've shown, together with others like Francois Lafond, that actually a lot of these trends are surprisingly forecastable. There are laws like Moore's law and Wright's law that make that true. So I think and this is another unexplored area in economics. Another key application that we desperately need are better economic models to steer us toward a sustainable economy. Current rates of growth are simply unsustainable. How are we ever going to do this without a huge crisis? I would argue our existing models are hopelessly flawed. And I think actually, since this is a mathematics lecture, I think what we're doing I think the ecology of the way mathematics is evolving. Stan Ulam was one of the pioneers of that. As a graduate student, we were pioneers. We started doing what we called experimental mathematics. We put equations on computers, we played around with them, we tried to map out the phenomenology to serve as a kind of scout for more focused theory. And I think that's increasingly the way things are being done and will be done in the future. I think that will happen in economics as well. And simulation needs to play a key role in between data on one side and sharper, small models on the other side. We need to be moving more towards, in economic, big science, because while I'm a strong supporter of small science, you can't do everything with just small science. Imagine if we were trying to deal with global warming without large-scale global circulation models. We just wouldn't be able to do it. Doing this is going to require a culture shift, and it's a big job. And I appreciate you being patient and listening to me. I'm 10 minutes over time. Thank you.